Yeah, we are going live now. So, good evening, everyone. Welcome to day 2 of our international webinar on quality by design. Before we go up with the actual session, this is for the participants who are listening through YouTube. We received a lot of queries or doubts regarding how to get the feedback form from our side. So you can see here for the people who are watching this session through their laptops or through their desktops, they can find the link in the description below the screen. But for those who are watching it in their mobile phones, you can see or you can take a help from this particular image that in your mobile below day 2 of this international webinar session, you can find a drop down menu like an inverted triangle here. So you need to just click on this particular drop down menu, this inverted triangle. So automatically you will be followed with the description here. So you find a description link at the bottom. So this option for today's session will be available around 8 p.m. today. That means during the question and answer section or at the end of the question and answer section. You need to just click on that particular link and then you have to fill and you need to submit it. So once you submit it, automatically we will get the response which is submitted by you. So once again, I repeat, this information is for the people who are listening to our session using their mobile phones. You can receive the feedback form at the end of the session in the description box. How to access it means you just need to click this drop down menu near to the session title and you will find the Google form link available in the description place. Just you need to click this particular link and then fill the form. Your response will be automatically submitted. Thank you. Now I request Dr. Shai Kishore sir to introduce the profile of today's speaker.
Thank you, sir. Good evening to one and all. This is Dr. V. Sai Kishore. Welcome to second day session of 3-day international webinar on quality by design organized by Innovation Cell of Bapatla College of Pharmacy in association with Indian Pharmaceutical Association Education Division. I would like to introduce today's presenter, Mr. Paritosh K. Singh, who is going to give us a talk on quality by design and statistical design of experiment. Let me give his brief biodata. Mr. Paritosh did his B.Pharm and M.Pharm from Jamia Hamdard University. Paritosh has been involved with scientific research in design and development of solid dosage forms with different generic and innovator pharmaceutical companies like Jubilant Organosis, Zydis Cadila, and Johnson & Johnson in the past. During his tenure, he worked extensively on developing formulations by using QbD elements for global markets. Currently, Paritosh is holding the position of research scientist in the multinational Perigo. We feel great to have you here today with us, sir. Over to Mr. Paritosh. Paritosh, sir, now podium is yours. Please go ahead, sir.
Okay. So, hopefully, am I audible and can you see my screen? Okay. So, thank you, Dr. Kishore, for this introduction and an opportunity to be here with the people, sharing whatever little I understand about quality by design and then statistical design of experiments. A very good morning to all those who are joining us here in US, and a very good evening, India. Delighted to be with you guys for the upcoming an hour. And in the meantime, I'll try to take you through this program. So the program for this session basically, I'm sorry for the disturbance here. Basically, what we are going to cover here is two parts. Basically, what is the quality by design, or what is as per the FDA, which is the Food and Drug Administration, the regulatory agency, and what is the expectations regarding the QbD, design of experiments. Sometimes, if I am not mistaken, people do take it into like quality by design as nothing but design of experiments only. So try to explain the very basics of what actually means, what was the genesis, how the design of experiments come into existence, why they are important, and then we'd like to have more of the discussion, the Q&As. I would like to have it throughout the stations, but then since I would be focusing more on the presentation part, Dr. Satish here will be taking up all your questions, and he might be organizing them and bringing them into me. So we would be focusing on the presentation. In the meantime, I would request the participants, those who are on the line, to submit their questions, their queries, and we'll try to answer each of them during our Q&A sessions. If by chance we miss any questions or any queries, definitely I'll be getting back to you using an email. During the sessions, I understand that it's Sunday and people are at the home, they're peaceful. So I would request your 60 minutes attention. And so hopefully people will be staying away from the emails and the messages in the meantime. Thank you so much again for attending this. Scope for the session, as I spoke initially, would be very basic to the desired pharmaceutical state. What was the vision of FDA? What actually design of experiments mean? What were the elements? I recall yesterday when I was in the presentation, Dr. Bhaskar took us to a lot of tools, especially the risk assessment ones. But I would be focusing here more on the role of statistical designs, how we use them, why they are so important, how their planning is important. And then I will touch base on very basics of two very well used and well known experimental designs, which are factorials and fractional factorials. And then if time permits, we'll try to see how we can think of the response surface designs and all. So since it's 2020 and we are still discussing QbD and DOE, so it simply emphasizes how important these topics are. But the seeds of this discussion were sown some 20 years back. If we see something around 2002, when the FDA came up with something of vision for the pharmaceutical manufacturing for the 21st century. And in the words of Janet Woodcock, who is a director of the CDER, Center of Drug Evaluation and Research in the FDA, they have a vision for the pharmaceutical manufacturing, which is an efficient, flexible, reliable, producing in high quality drugs. And in turn, what they have offered to the industry, to the people, is a greater regulatory oversight. So we can say that the genesis of pharmaceutical QbD started as a vision in somewhere in around 2002, where they thought, how are we going to manufacture, how we are going to bring changes into our manufacturing pharmaceutical manufacturing in the coming decade, that is in the 21st century. In essence, if we say the goal is to have a pharmaceutical manufacturing in the 21st century to be entirely based on quality. So it's a quality driven. The question is we are not having quality products before QbD into existence, because pharma is not 20 years old. We have been there for a very long time, and we have been producing some quality products wherever in the market. Now, US FDA is a agency, regulatory agency, which takes care of the medicines and the sale and the research of medicines, drugs in United States. And they felt 20 years back that we as a pharmaceutical industry are not catching up with advancements in science and technology happening throughout the world. QbD as a term was a concept by Joseph Joran way back in something 1986, 88. So why we are talking now for QbD in pharma? So as I told you earlier, the FDA felt that we are, as a pharmaceutical industry, was not in sync with the landscape of technological improvements happening. And they just wanted to encourage the innovation in the pharmaceutical manufacturing, which was very stagnant because of the stagnancy in the regulatory regime we have earlier. Also, it was felt that the increased testing does not necessarily improve the product quality. So what can be done? So quality must be built into the product, and how it is possible. The specifications we generally have for each and every product should not be stagnant. They should be based on the mechanistic understanding of how the process or factors affecting the product performances. So how they want to achieve that? By incentivizing the optimization of new innovation in science and technology in the pharma. For example, nowadays we see there's like continuous manufacturing, there are real-time release testing, there are advent of non-destructive tests like NIRs, there are predictive tools available in BE. And in turn, they offer a regulatory flexibility if we are able to show them that we have a better understanding of the product, the process. So I would like you all to see how many times this specific word understanding is being used throughout this presentation. So when we'll reach the last slide, we'll try to, or you might understand that why this one word is so important when we talk of QbD. Moving to the next, in 2002, the vision came of pharmaceutical manufacturing in the 21st century, and then we have a lot of guidances coming from the US FDA. The one was ICH Q8R2, wherein the pharmaceutical QbD was actually defined, and how it was defined as a systematic approach to the development, which begins with predefined objectives, emphasizes the product and the process understanding, which is based on the sound science and the quality risk management. Now, I probably borrowed it from the ICH Q8 guideline. These objectives, like systemic approach, predefined objectives, product and the process understanding, were actually brought into practice by the following. A systematic approach was desired, which started with thinking, the mentality, which started with the begin, the end, the mind. So we'll start thinking the last step. Predefined objectives, and that was brought into the development using two specific key things: the quality target product profile and the CQS, which were identified based on the QTTPs. The product and the process understanding were actually brought on paper on the surface by identifying the critical material attributes through using various tools of risk assessments, and the critical process parameters were identified and studied. The ultimate aim of any risk management or any QbD is to have a process control or a control strategy in place, which can take care of all the variations happening. And That's why that has been taken care by the FDA by they emphasize having establish of appropriate control strategy in place should be there with every ANDA or NDA filing process. And similarly, there are like sound science because they are supporting science-based submissions and the various risk assessment tools to figure out the risk criteria. So as we have identified the QbD-based elements like QTTP, the product and the understanding, the process understanding, having a control strategies in place, the expectations were very clear. The expectations were like in the QTTP, you need to identify the CQs. When you talk of the product and the process understanding, we have to identify the CMAs. We have to identify the CPPs. We have to identify and look for the scale-up principles. We have to link the CMAs and CPPs to the identified CQAs. The control strategy contains the specifications for the drug substance, the drug product excipients, and each and every step should have the control strategies in place. And now the life cycle approach has been into practice. Like it's not only the development does not end with the filing of the product or being an approval, but throughout the life, the FDA or the regulatory agency want us to understand and do the modifications as we get more and more learning from the product. So if you can't explain something, you don't understand it well. And as I told you at the beginning of my presentations, we have to see how many times we're using this word understand. And if somebody asks us, what do you mean by understanding? Everybody has their own way of explaining things that they understand. But when do you say that you understand? So a process or a formulation, of course, or anything, maybe in analytical. So we are here generalizing that as a process. A process is well understood when the three criteria are met. First, all the critical sources of variability are identified and explained. So it's not only the identification of the variability, but there needs to be explained. You should have a process in place which will manage this variability in itself. Means the process should be capable enough to manage the change or the inherent variability, and the quality attributes identified can be accurately and reliably predicted. So here the role of predictive tools, the analytical methodologies are very important. So all these three combined together, when we have a tick mark for each and every step, we can say that this process is well understood. Now, how to establish that product and the process understanding is important. How we do that in actual practice. So the first step would be definitely identifying all the possible inputs here. In the whole of the presentation, we might be giving different names like input, like factors, or independent variables. Once we identify these factors, we need to establish the levels wherein we can use them, or especially for those materials which are identified as high-risk items. Once we establish that range, we need to conduct experiments. And here the tricky part is, as suggested, we are doing a QbD here. We'll say whenever possible, you do an experiment using a statistical design of experiments or use a design. But we also appreciate that it's not every time possible to do that. So it's based upon your understanding when we can use a DOE or when we can use other methods of experimentation. Once we have these experiments done and the risk assessment and the scientific knowledge has been used for high risk material attributes. This tool is very significant, and I think Bhaskara in yesterday's presentation, we see he has explained very beautifully the risk management part. The analysis is again the very critical part. The experimental data has to be analyzed using statistically, and we have to be very sure of whether the attributes we are talking of, we are learning is whether it's critical or it's not critical. And we have to decide that leaving our biases altogether, that should be a criticality and non-criticality should be based on the sheer experimental data and not our thoughts. I have seen sometimes when we say that we are running in a simple experiment where we study the role of a binder, and sometimes it seems that even the increase in the binder concentration is not slowing down the dissolution, which is against the usual thought process that increase in the binder concentration must decrease the dissolution or some other factors. Now we have to move away with this mindset. Once we are trying to analyze, trying to see the data, data should always be, the analysis should always be data-based. And ultimately, with all these factors in place, we know how the product and the process is behaving. Ultimately, we need to identify and establish a suitable control strategy in place so that whatever variability we have observed should be taken care by the system, and we don't need to manually every time do the changes in the composition or the process or the parameters. A very important aspect for a QbD comes around in ICH Q8 only when they talk of a concept of a design space. Now, why I'm bringing it here? Because it's very interesting. We use design space basically in every ranges we establish. We say that we have got a design space in place. Look at the definition. What it says is the definition in the ICH Q8 itself says is a multidimensional combination and interaction. And mind these two words very important: the multidimensional combinations and interaction of input variables and the process parameters that have demonstrated to provide the assurance of quality. Here, the word interaction is very important, and that actually drives us towards this question: why actually we need to do a DOE or statistical designs for experimentation? So design space here we can say is a direct outcome of a DOE data or the validated models. So in general, in the regulatory term, we cannot identify any given range as a design space until it has been developed using a validated model or a statistical design or a design where we have studied the interaction part. And that is obviously to all the viewers, we know that the design space may be scale and equipment dependent. And that's where the scale up impact, the scale up knowledge and how actually scale up happens, what are the challenges, and then we have very scale up principles in place to understand before actually adopting the DOE data from one scale to the next scale. So this is all about QbD, why QbD was here, what are the elements of QbD, and why actually pharmaceutical, why we are actually today in 2020 talking of a pharmaceutical QbD, although we know that this is an extensively used term in every other part of the world and every other part of the industry. So either we generally, we are in anyone in the research area generally do experimentations, and any experiment you plan basically has two specific parts to that: a strategy and a purpose. Whether it's a statistical design or whether it's any other, this remains constant: the strategy part and the purpose. So strategy is for setting of experiments in such a manner that the information actually we obtain is very efficient and precise. And obviously, the purpose is to determine the relationship sometimes between the factors, here we say, are factors like you say with the input variables, or we say independent variables, which we want to study for the more simplicity, a binder or disintegrant or any other factors. If in analytical, we want to understand the diluent ratios or the solvent ratios. These are all called factors on the system, and the response of the system. Response here defines what you are going to monitor. So for example, a tablet or in the formulations, generally, our responses are the dissolutions, the hardnesses, the friabilities, or any other characteristic of the tablet or capsule or any other dosage form. So these factors in the responses basically are very specific to each and every dosage form or the unit operation which has been taken up for study. So the scientific methods in day-to-day life in the experimentation, we are using the scientific methods to carry out our experiments, and that scientific methods can be like a trial and error sometimes, or we generally use changing one factor at a time. This has been the most extensively used kind of experimental plan we have. Or moving to the next level, we move on to a structured experimentation wherein we choose a behavior, we set a goal, apply some techniques, softwares, find a plan, and then we statistically analyze the data. So an approach for very effective and efficiently understanding the cause and effect relationship, or you can say the factor and the response relationship between the process variables and the responses, is what is called as is the ultimate aim for any experimental design. The question came in why the statistical DOE? Well, I'll just take back you to the few slides back when we were defining the design space, and it talks of experimental plan where we can study interactions, where it is multidimensional. I hope you guys remember that. So statistical DOE is a tool which use the scientific art or the knowledge gained through our years of experience into a complete science-based decision-making process. The methodology remains, it's very well known to most of us. Those of you attending here, we know that with the statistical DOE methodology, we have to first select a specific design. We have to conduct or randomized experiments based on that design. We have to analyze the data using the ANOVA or other facilities available in specific tools. And then, depending upon which part of the design we're using, whether it's in screening, whether it's factorial or factorial, response surface, mixture designs, we will definitely create a multi-dimensional space or a model. So it's about modeling. Now here, let's take an example of the simplest usual kind of experimentation we do. This is an example of extrusion asphyrination manufacturing process, where we want to produce the pellets for further using the compression or coating, in compression or capsules, whatsoever dosage form we want to make. If you can see here, we have several factors. What we want to study, the objective should be very clear. And the objective of this experiment is which of the following factors, we have got 7 ones here, has a large effect on the yield of the pellets of the right size in order to select on the further studies. And we have the percentage of the binder, amount of water, granulation time, asphyrination load, asphyrination speed, extrusion speed, asphyrination time. So these are the factors of the input variables, or we can say independent variables. And we have the labels here marked. Labels means at what ranges we want to study that. And there is a lower limit and there is an upper limit. So one safe example, we are moving into the lab with this set of experiment. What we'll do definitely is we'll try to see which of these factors has a large effect only. And so it's a simple basic screening type of thing. What usually we do in an OFAT method, we conduct an experiment one, which is called as a base experiment, where we take all the factors at the lower limit and conduct an experiment, and we'll have the data. Next experiment, when we try to understand the impact of the percentage of the binder, what we do is we keep all the factors at the lower level and use the percentage binder at 1% here, the upper limit, to understand its impact. And now, if we want to see, and that we do for each and every factor. Similarly, for the granulation time, stagnation load, we'll keep all the rest factors at the lower limit and the factor we want to study at the higher limit. How we provide the inference for that? Say, for example, if you want to understand the impact of the binder, we simply will go to and we'll subtract the values obtained from the experiment number 1 from the experiment number 2. So all in all, we did 8 experiments to understand this effect, and ultimately we are drawing our conclusion using 2 experiments only for each factor. The first one, wherein all the factors were the lower limit, and the second experiment wherein that specific factor or the parameter has been kept at the upper limit. Now let's see what happens is what the problem we face. So as we have seen that we carry the base experiment, we follow up with the rest of the experiments, 8 number, and influence of each factor is determined by subtracting the base experiment from that specific experiment wherein that specific factor has been kept at higher ones. What is the advantages and disadvantages of this tool? The advantage I'll talk of, it's very quick. We can do it right now, by the way, kind of very fast. The disadvantage, effect of any factor, if you see here, was calculated using just 2 experiments. Although you had carried out 8 experiments, the response for each factor, the effect is calculated only from 2 experiments, and that we can say as a poor precision. Now, since we have not studied, we have not taken into account the other factors into the experiments or into the conclusion, so the influence of other factors in determining the impact of any other factor is not taken into account. In simple words, we can say there is no study, there's no effect of interaction effects studied here. We don't have any data on what would happen if we messed up or if we have 2 factors interacting. Now, the most important factor here is, what if, suppose the experiment number 1, which when we have kept all the factors at the base level, goes wrong? All the conclusions would be in very or wrong, and we will be guided in a very different direction. So in summary, we can say that our OFAT method is it's not a bad design, it's still a design, but what we can say is an OFAT or changing 1 factor at a time method is an inefficient design. It may give you misleading results, and absolutely there is no data on the interaction effects. And if you come out good, we have a successful experiments, I can only say that you just got lucky. So what could be an alternate strategy? The vision for the 21st century pharmaceutical manufacturing has a vision that your experimentation plan should be based upon how well you understand your process. So based upon where you are and where you want to be in future, based upon what kind of information you have today regarding the process, the formulation or analytical techniques, you build on your knowledge using different experimentation plan throughout. So here, each step wise, say from the screening, each step generates information for the next level. So initially, during the screening trials, we determine the important factors, and then further, when we move into an optimization trials, we try to optimize that using those factors which are only very important. But hold on, once DOE is good, design of experiments are good, but there are real challenges to that. We need to ask ourselves probably before initiating any experiments, like, are the needed resources available? So DOE is it's a plan wherein you need to understand, do we have the resources to do that? Once we need, are the process requirements clearly defined? You have to be very sure what you want from those experiments. What is the extent of process understanding? It's not a blind game. It's not like you just put something on your eyes and just do a DOE and it will give you some magic bullets. No. What were the deliverables? How you measure your response, that is one of the most important tool. Do you have a validated analytical method to identify those responses? Because what if you don't know what you're monitoring and how you are monitoring, that will jeopardize a very good design itself. Is it really required? That's a good question to ask at any minute time. Does it meet our goals? Do we really need to do a DOE? And definitely, risk management nations, we should see whether we need to do a DOE or we don't need to do it. What is the risk? Answering these questions will definitely help us in determining if actually the DOE is appropriate at this time. Now, the basic steps, very clear. Define your goals and objectives. Determine what is known. Select the input levels, factors we want to study. This is very important when we are selecting the labels. Your labels or the ranges for the factor study should not be very narrow. It's meaningless if you want to do a meaningful DOE. And it simply means that, for an example, if we want to understand the impact of a binder or a disintegrant, the ranges should not be very narrow. We should have a sufficient range to study. Once have all these in places, we need to select the appropriate design. Obviously, we need to run the experiments. Further, evaluate, define next steps, and an implementation plan that control strategies in place. Three things, in summary, needs to be done very right. We need to identify the right objectives, and hence that will help us to define or identify the actual design type we want to use. We have to select the right factors or variables and the right responses. So if you want to study a tablet, there could be 1,000 of factors, but it's your choice. We want to study the friability or the dissolution, which is more critical. So till here, we moved from QbD, why QbD was important, why we do QbD. Here, we learn DOE, statistical design of experiments, why we need to do a statistical design of experiments, what are the steps, what needs to having a plan for a better results from us design DOE. And so in summary, we can say that a statistical DOE is a very structured approach to quantify the effects of factors on the chosen responses. The benefits are very obvious. It increases the process understanding. Now go back to the first slide where we say the agile, in 2002 or 2004, what QbD director is saying. We want manufacturing which is efficient, where we understand the process, talking of regulatory flexibility. Now, understanding again here, somehow it seems that a structured way of experimentation provides us a better understanding of the product and the process itself. Interaction between factors can be identified and quantified. Again, I'd like to take you back for a moment to the design space thing. What talks about a multi-dimensional space? It talks of interactions. which is only possible with structured statistical DOE and not using an OFAT method. Obviously, if we use higher designs here, like response-first methodologies or other factors, we can optimize and we can establish a mathematical correlation between the different factors and the responses. So it's a database. Well, after we understand that DOE is important, we understand DOE should be used for its specific obvious what's called the benefits of that. Where are we going to use them? There are a number of number of designs. So selection of a design is specifically based on the quantum of information we have at the time when we are planning the experiments and the stage of the development. So whether we are screening a design, whether we want to characterize it, whether we want to optimize it, or whether we want a confirmation of the chosen process. And depending upon these factors, specific design can be selected from the available designs, which are factorial, fractional factorial, response surface, and mixture designs and all. So ultimately, the approach should be the approach of selecting a suitable design should be dependent on how much we know about a specific process at that given point of time. Now, I'll just like to go in very brief in the interest of time. I think we'll be running out of the time shortly. So I'll just like to bring you some basics of or why we use these two very well-known designs used in practice, the factorials and the half factorials, and maybe a slide on the response surface methodologies. A full factorial design is, I think, it's basically a screening design, and it's meant to be used when we want to screen something, when we want to screen a few from a lot. So we have, say, for example, if we have 10 factors in an experiment and we want to screen them, and if we use RSM design, that won't pay you. So that's where the importance of objectives comes in here. So our objective is screening. We use either full factorial, or let's say further, what would be the challenges when we adopt this technology. So what is a full factorial means? A full factorial design involves all the possible combinations of the factor, all the possible combinations possible. So this is one design wherein we will get a maximum number of experiments. Second important thing about this is a full factorial design works at two levels only, a low and a high. The nominations given here as minus and plus, and if you see here, is definitely just to show the levels. It's either at low level or at a high level. Also, very important here to notice, if we see a pattern. So if we have a number of factors, we can plan using our pen and paper the actual sequence of experiments for a factorial designs. That's why it becomes so easy, and it's the simplest design to use. We can look at the patterns here, like minus plus, and then in the second is minus minus plus plus. Moving to the third factor, it's 4 minuses, and then last 4 plus, and so on. If we go on increasing the factor levels, it will go on like that. So it is generally denoted by 2 to the power n. So as we increase the number of factors, so before we go there, if we see for the say 3 factors, if you want to study how it will show up in space, or if you can visualize the area wherein we can actually anticipate the responses by a cube in case we are using a factorial design. So with 3 factors, the whole space inside the cube is accessible. Whereas if we see the OFAT approach with almost half the number of experiments, you see they are linear in every directions. So generally, we cannot say that what actually happens between these spaces can be accounted for. Going with the same design, comparing the 3 factors, if we see how much space is being occupied if we do an OFAT way of doing experimentation, changing 1 factor at a time. On the other hand, there is a whole cube here with 8 experiments. we see that just less than half or even less than that area is covered using an OFAT method of experimentation. It simply means that it's just a visualization tool to tell us the efficiency or the efficiency of a design. If we compare factor-wise, you see if the number of factors increases, the relative efficiency of factorial design goes higher and higher and higher. So there's a myth which says that I can say it's a myth that for OFAT methods, OFAT way of experimentation is the least expensive, or we have to do a little number of experiments. But then we have to see that we are compromising on the information or the amount of information we can have from those experiments. And if we talk in terms of efficiency, here we can say from a simple experiment that this statistical based design is more efficient as compared to any OFAT experimentation plan. So in the nutshell, what we can say here is, if we compare the OFAT way of experimentation and a simple factorial design, the effect of each factors under many more conditions is studied using a factorial design approach. This approach will provide us a look on the interactions, and obviously, as we see here and summarize, like as we go, as the number of factors go on increasing, we have more and more we have an increasing efficiency levels for the same. Well, now we are struck. So how many factors we are going to study if we want to use this factorial designs? As we have seen earlier, that as the number of factors or the independent variables go on increasing, the number of experiments exponentially increases. And so at some point of time, it really becomes not possible to do those experiments. So simply, for example, we see if we have a 5 number of factors moving to a 6 number of factors, the number of experiments jump from 32 to 64. It's huge. And that here comes the resource availability. Are we going to do that many experiments? Do we have the resources available? So here the question comes is like, is there any way to conduct a statistical DOE and not compromising the information required from that? Still, we manage with a fewer number of experiments. And the answer is yes. We'll see in the next slides in the coming up. So just to summarize about the factorial approach here, as we have seen that with an OFAT approach, potentially it might give us a misleading portions results where it doesn't consider all the factor combinations and interactions. Whereas the full factorial designs, it covers the entire experimental space. They are easy to lay out. We have got more informations, and the most important, we can have a interaction data for the different factors. So just to answer the questions, can we have lower number of experiments with increasing higher number of factor studies? Yes, there is a substitute, and we refer to it as a fractional factorial designs. What we do here is, as we have seen that a factorial design gives you a set of experiments with all the possible combinations. As we go on increasing the number of factors, the interaction goes higher. Say, for example, of 5 factors, we'll have interactions of experiments of having interaction for all the 5 factors, the 4 factors, the 3 factors, which is merged with the main effect. In pharmaceuticals, we recognize that the higher order interactions greater than 2 are not important at all, or maximally 3. So if we can exclude those experiments in that design, say for example here, for the 10 number of factors, we have almost 1,000 number of experiments which goes for a higher order interactions. So if we just remove that, we can successfully bring down the number of experiments required to study the higher number of factors. Obviously, it definitely depends upon what we want to study. Is it the screening or is it the optimization? So this is a simple comparison of for a 5-factor experiment where we're doing a full and a half factorial design. You can see here for full factorial, we have almost 50%, the 16 experiments, which are used to provide the information around the 3 factors, 4 factors, and 5-factor interactions. When we just remove those experiments which provide these informations, the design becomes a half fractional factorial, 16 runs, and it does not compromise on what information we need, that is, an averages the main effects in the 2-factor interactions. So with this, I'll just try to, with this, we come to the end of the factorial part. And then in very brief, one of the most important designs which we use for optimization is known as the responsiveness designs, which are nothing but they explore the relationship between several explanatory variables. And if you see here, as you've seen with the factorials, we study at 2 levels. With the responsiveness methodologies, we can move up to 5 different levels for each factor. And sometimes there are designs like central composite design where we can actually explore outside the ranges which we have studied. For that, they're specifically known as the axial points in the design. So the main idea is to use a design experiments to obtain the optimal responses. So that's why it's used in optimizing whether it's process or a formulation. These are multivariate polynomials, so we come across a linear quadratic equations in these models. They are strictly good models to study once we are like very much sure of all the effects, and there are only few factors which are there to study, and just we want to optimize the process finally before moving to the next level. So with this, I cover my brief introduction on the designs. Till this time, we have covered almost why we want a QbD, why DOE is required, and in that DOE, now we are covered like a factorial design, responsiveness designs, why half fractions are needed, can we go for half fractions if required. After that, I just want to cover the 2 basic things which actually I found many of most of the time missing from the experiments, or like people don't pay heed to, and they are like center points. The center points are very integral and important part of any design experiments. It definitely gives us an idea of the estimates of the curvature, whether our design is linear or there is a curvature. We won't know if we don't have center points included in the experiments. What is the pure error or the general lack of fit in while we are evaluating the factorial designs in the ANOVA portion we see. So we should not try to move ahead with any compositions without any center point runs. And if points, definitely it needs some additional resources, but that is worth of it. And the second most important thing I found very interesting is the question about the replications. Do we really need to go for the replications? And why replications are needed? Replications are very important to give a measure of the pure error or the common cause variations. When we replicate, it provides us a greater assurance regarding the significance, and ultimately it improves the power of your statistical design. So with this, I'll try to shut up and I'll finish my presentation. There are many things I've kept in the backdoor slides, but I think we are running out of time. So this is all from me. I'll just finish it by summarizing few things. Like I just try to reiterate here is we need to understand that quality by design is not DOE, and DOE is just one of the tools we use for QbD. Following the QbD ensures a higher level of assurance of product quality and facilitates innovation. File first, learn later approach may not be working anymore. We need to be very thorough with our development. DOE is not a substitute for a subject knowledge and experience of the processes, right? It's not a wonder pill. Combined with the process knowledge and experience, this knowledge of DOE becomes a lethal tool in the hands of an experienced researcher. So I just wanted to picture what happens when these two combines. We know what actually RAM did, or what is capable of. I'm Every experimental situation is different. One size does not fit all. So experimental design selection should be very thorough and should result after brainstorming with the subject matter expert. DOE is too complex and it requires far more experimental trials is just a myth. DOE is not a design expert scrambler or JMD. It needs to be understand basics before jumping into the software. And either we love it or hate it, the statistical designs of experiments is the way of experimentation going forward. So at times we better learn it and live with it. It is going to stay here. Thank you so much with this. I actually appreciate all your patience and stay safe. Now,
thank you very much,
Satish.
sir. Yes, sir. Thank you very much. I think you are both summary slide answered many of the questions. Hello.
Yeah.
Yes, sir. Sir, I have a few quick questions. So before you take up the questions to the participants, we need to give a small announcement that along with Dr. Paritoshing, we also have our senior professor, Dr. Nagaraj Garu, working for Padmavati Mahila Vishwavidyalaya, Tirupati. So he is also there in our expert panel today. So we request the participants to kindly make use of the expertise available, both from today's speaker, Dr. Paritosh, and Dr. Bhaskar Rao, who is also there. And we also request Professor Nagaraju Garu to address the participants with respect to this DOE concept in the academic side. So now I'll share a few questions which are asked by the audience, sir. Example for certain input variables and the process parameters. Mr. Paritosh.
Yeah. Okay. So can you hear me, Satish? It was breaking a bit. So you want some examples for the factors and the responses? Satish, did we lost you? I can't hear you.
It appears that Dr. Satish is lost.
Okay. So Doctor, what's your question? Like, you want some examples for the factors and the responses?
Yes, sir.
Okay.
Yes, sir.
Right. So it's a good question actually. So for example, if you take any example of, say, for example, you take a tablet manufacturing, right? And we have, say, for example, we have a disintegrant, we have a binder, we have a diluent in that. This is the most common, simple example. So say, for example, as a binder, we have used povidone. We have a disintegrant, we have used SSG, or sodium charged glycolate. And as a lubricant, we take magnesium citrate, right? So these becomes of factors because these are the things we want to study their impact on tablet. Now, what we want to study the impact on, what we are going to measure, how we will identify their impact is called an responses. So the response would be, say, for example, for your binder and a disintegrant is a dissolution or disintegration. So selection of the factors, lubricant efficiency. Again, we know that lubricants may impact the dissolution. So our response could be a dissolution. It may be another ones, like sometimes with more of the lubricants, we see a problem with the compressibility of the blend. So here in this case, your compressibility can be also a response.
Yes.
So am I able to answer this question?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Now the second question is interesting one. Like, will there be a DOE expert in each industry, or in other ways, what are the job opportunities related to this particular area of expertise?
So an excellent question. So under my first slides, I said pharmaceutical manufacturing vision 21st century, right? We are the ones who are least using QbD. QbD and DOE has been extensively used throughout other you can say industries. There we talk of Six Sigma, air flights, or any other industry. They are using it extensively in the car manufacturing everywhere. And nowadays, when we say that QbD and DOE is going to stay here, there are ample opportunities. In every industry now, in every company I see now, there is a statistician. And suppose if people coming from the pharma moves into that, right, they would be an ideal candidate, because a statistician understands the statistics, but don't understand the formulation or the pharma, right? So sometimes they would be like creating an experiment saying that probability of moving from 0.2 to 0.5 would be very significant, and will make a design a big hole around, like it's very significant thing. But a formatter understands, or we understand as a in the pharmacy business, that it's not that significant. So our knowledge of the pharmacy, the pharmaceutical fact, the pharmaceutical technology, with this statistical tool, it's going to stay. It's a lot. I see a very bright future for this.
Sir, there is one more question, like how can we address and control unknown factors using this QbD method?
So things which I didn't cover here is like the lurking variables you're talking of. Actually, there are few variables called as lurking variables, and that is why when we say a plan and experiment, and then there are many concepts like blocking. So if we say, for example, we have 16 experiments, we know that we cannot do it in one day. So what we need to do is we need to prepare those experiments in blocks, and there is an option of blocking available with any of the tools you use. So that's especially put your the required what's called the design into different blocks, say 4 blocks, 5 blocks, or 6 blocks, and that blocking actually negates the day-to-day variables which you call as a lurking variable, which you don't account for, which probably sometimes you don't know about coming into the design. So that's a very important question. I have found that most of the time we have a number of experiments, and then what we do is we never think about that. We keep on doing that without actually applying blocking into the experimental part, and sometimes it goes haywire. Yeah.
Sir, the other thing is, along with a lot of appreciation for your presentation, so many of them has for a fake topic. They requested for a exclusive demonstration session.
Anytime, Satish, and I would be happy to do that whenever you want. Let us know. We will try to do that.
Yes, sir.
I would be more than happy to do that.
Yes, sir. Because once you present a demo to the participants, I think they can get their doubts clarified in this particular area. There are a lot of appreciations, and there are many other questions. But now, with your permission, I request Professor Nagaraj Garu to give his expert advice regarding how to use this DOE or QbD aspects with respect to academic research. Professor Nagaraj, sir.
Thank you, Dr. Gopalakrishna, and also the today's speaker, Mr. Partoshi. I want your summary slide so that it will substantiate the audience can see. Mr. Parsod, can I have your summary slide, last slide?
Oh yeah. Is that you're looking for?
Yeah, that's right. At the outset, it gives me an immense pleasure to listen to you people actually who are involved in the helm of affairs in the actual field of work. There is a pharmaceutical industry where yesterday I listened to Dr. Bhaskar and today I listened to you. And it is such a beautiful and good presentation where it is easily understood by an M.Pharm or a UG student or PG students. So sitting on the other side as a senior teacher, and as you rightly said in the beginning, catching up with the technology is the very, very important at any stage of their life, including teaching, what we are in teaching, what the students are going to learn, and how we are going to go ahead with this technology is very, very important. And many a times we apply the students about the need of catching up the technology. But however, when the person like you, who are the actual employers to our students, if you emphasize such things, definitely there will be a lot of change in our students' setup and attitude to take up this particular area more seriously. What I would like to add upon to you, the students are expected to know the basics of this, what Mr. Partosh Singh has already explained to you in a good presentation, a nutshell presentation. You should know at least the various terminologies like PTPP, COA, CMA, CPP, CQA. These are all the language where the students should speak to the interviewer. If Mr. Partosh Singh wanted to give a job to a person in his R&D in formulation development, if the students don't know what advances technology, what he's using in his lab, he can't spend all of his time to train the student. The student have already obtained a training in the college for 2 long years, and he wanted to have minimum incubation period, probably 2 to 3 months. A crash training is enough for the student so that he should be put into the exact time. So the students will be employable if they have been equipped with this type of technologies and capturing the technologies, understanding the need of the pharma industry, not getting the degree or obtaining a fancy degree from fancy university. Apart from that, these are all the basic things where they will it will be appreciated. Many a times the students will have the inhibition that when you try to teach them in a regular class, this DOE and QbD, they come with the things, sir, I am from a BPC background, I don't understand the mathematics very well. But your summary slide says that, very, very nice. DOE is too complex and requires to far more experimental trials and far more knowledge. It is a myth. So don't jump into the design expert directly, but it needs to understand the basics. That's what we try to. I would like for the students who are listening to this talk, who are doing this, your importance is need to understand the basics before jumping into the software. Then link the basics in the college, what you have got, and then get listen to lectures out of the box like this and interact with the people like who are actually doing this, and then acquire a knowledge. As I was telling in my beginning of my talk, make you employable. These are the things which make you employable. It is not the degrees what you have got with the first rank and whatsoever it is going to be. And to the audience as well as to the esteemed speakers, we do in our university, especially in pharmaceutics department, we all do this at the MPharm second year level project presentation, project going, what is it, project work, dissertation work we call it as, and we give in a simple way how we are going to take up this formulation development using DOE technologies. So I have been overwhelmed with the simple language of Mr. Partosh Singh. It is very simple and crisp and point answer to what do you call, the students will definitely remember. As Dr. Murthy was telling, this is available at any time on the YouTube channel. Probably I recommend to all the young teachers as well as the students, go back and again listen to it. And it's such a pleasant to listen and understand this and develop an interest in that, and again use the Partosh Singh's word, move ahead with the technology. The technology, catching up the technology is very important, and where that gives you a good job and a good future, a good opportunity to work for that. And with these few words, I profusely thank the speakers. I had really a great experience listening to you who are thousands of miles away. If I am not able to use the technology of the Zoom or the Skype, and I say, no, I am retiring in 2 years, why I should know all this? Then I would have really missed all the interaction from you. It is very difficult to catch you. You're thousands of miles away. And also the people around in a beautiful country like India, the length and breadth of India, it's very difficult to bring in all the people on one platform, thanks to the technology. And I quickly adopted this technology, and I'm effectively using this for the regular teaching purpose and assignments, where, to be frank, we have been forced to learn by the UGC. So with these few words, I thank Gopala Krishnamurthy Garu for giving me this opportunity. And I recommend to the young students as well as young staff members, please attend, interact profusely with these people who are helm of affairs, who are doing this in a this type of works in the industry where they are going to be and understand very well. Thanks for the opportunity given to me.
Thank you, sir. On behalf of Bapatla College of Pharmacy and Bapatla Educational Society, we wholeheartedly thank Professor Nagaraj Garu for addressing the participants, especially students and young teaching faculty members. And since we are running out of time, still there are many questions to answer. With the request to all the three speakers of this international webinar, along with Professor Nagaraj Garu, we also request you to be there for tomorrow's session. And if possible, let us have a panel discussion on this particular topics. And a special request to Dr. Paritoch, make yourself available to make a demonstration on this DOE software.
Sure, Dr. Satish. If you have got 2 minutes, I just want to convey that
please.
I have this terrific time here on this webinar, and we wanted to take up many questions as far as possible. So whosoever, if we are not able to answer those questions, I'll be more than willing if you can just mail me those questions directly. We'll get back with the answers to those questions. Anybody who would like to know something more about this or on the resources, there is a mail ID there on the SharePoint itself. They can mail me, and we'll try our best to get back to each and every query here. With this, I actually would like to thank you all. My sincere gratitude to Dr. Gopalakrishnan, Yukishore, John, and Satish for providing me this beautiful opportunity to interact with this exciting people there. Thank you so much. I look forward to more sessions with you definitely in the future. So thank you.
Yes, sir. Thank you very much. And thanks a lot for all the resource persons who are available till then. Have a good day, sir. Thank you.
Thank you. Thank you.
Thank you, Ananda.
Thank you.